Can you guys mute? Okay, thank you. All right. Let's give 1 minute so other people can sign in. Yeah, please mute yourself. When you want to ask a question, you can open the mic again. So we are recording, and today is week 13, lecture B. It's a Friday. Let's look at the syllabus, okay? Let me see how many people are online right now. 10. So you can see that we are in week 13. We are in week 13. So week 13. We are in the sensor part. We are going to start at the sensor part. And next 2 weeks, we are going to focus on sensors, actuators. Okay. Then the last week, I'm going to show you some of the advanced controls in mechatronics and some examples. Maybe we'll do a little bit on PLCs. So because that would be good for your job interview. Say, oh, have you learned a little bit PLC? So I'm going to give you some exposure on that. So you can say, oh, we mentioned it. So let's start. Let me see, we have 13 students there. So, okay. Introduction to sensors. As you know that if you want to count how many types of sensors in the world, the answer is hard to count, okay? There are just so many of them. You want to sense a lot of things, okay? Do we have a sensor can measure how happy I am? Maybe one day, okay? So there are a lot of need about sensing. Right now we need a good sensor about the COVID-19 infection, right? So we're going to cover the types of applications of measurement instruments. We need to ask a question about sensing for what? And we're going to have a general discussion about the configurations and the functional description of those measurement devices. So what are the types of measurement? So, or we want to say the purposes. Well, what do we want? What purposes? So basically we have 3 big categories of purposes of sensors. The first one is sensing for what? To monitor the process and to monitor the operation. Is everything okay? So that monitoring, okay? So sometimes people say, oh, everything's going well, but how healthy it is. It's called health management, okay? So that's first purpose. The second purpose is to make things under control as we wished. So when we say control, you should have a picture in mind. So you have a desired reference, you have feedback, okay? So then you make this arrow as small as possible. So this is called make the process under control, meeting our control objectives. So to be fast in transient, small or zero in the steady state arrow, and so on and so forth. Okay. So these are monitoring, control, and what? And to help to analyze the experiments, to have discoveries. So let's say discoveries. So you do have a sensor, you do experiments, and you make discoveries to understand the relationship, engineering cause and effect, okay, and so on and so forth. Okay, so 3 purposes. You should be able to say 1, 2, 3. Okay, 1, 2, 3. So we are going to elaborate each of these. So for monitoring, so you have applications, measurement instruments characterized as essentially a monitoring function. Okay, a monitoring function. You do not really take actions based on the monitoring. It's just to see whether everything is running properly. So you don't do a real-time feedback decision-making based on that. So it's only for monitoring, okay? Because majority of time is in good operation, is everything is normal, but in some cases, you know, you may have something off the limit, so you send out alarm. So that's not for control. So be careful. There's difference between monitoring versus control. So like thermometers, barometers, water, gas, electric meters. So you have lots of sensors in your house, right? So you have sensors to measure how much gas you used, water you used, electricity you used, and temperature in the house. So to do control, okay? So that's monitoring. The second is to do control, component of a control system. It is a component of a closed loops. Well, we see here, which is a closed loop control system. Control any variable in a feedback system. Necessarily, you have to measure it, okay, to measure it. We are going to discuss about if you wanted to have a good control, you also need to have a good sensor, okay? So of course, this is true philosophically. So there's an interesting saying that if you cannot measure, you cannot what? You cannot manage, or you cannot control, okay, and so on and so forth, okay? So measurement is very important everywhere, and it can be specifically as a variable. It could be a measurement of performance of your team, okay? Then measure that, you will be able to manage, okay, to manage. So a single control system may require information from many measuring instruments. So your decision could be based on multiple sources of information. Like in industry, industrial machine and process controls, aircraft controls, and so on and so forth. And your dishwashers, your washing machine, and your dryers, so they all have control systems inside. So this is the first and the second purposes of instruments and sensors. So just give you the third one. We haven't actually thought about done about this. So you design experiments, you find out new sensors, and so you can have new discoveries, which is also very important. But let's, as mechatronics people, we focus on 1 and 2. Okay, that's why we explained here. So let's take this big picture. So this is planned to be controlled So you have some disturbance input in here. It could be go in front, it could be go after, okay? We put it in the middle, it's fine. So then we have the output. We usually say, I have output Y. You have an input U, okay? Input U. And you have disturbance D, okay? Disturbance D. So, but in process industry, they call Y as a controlled variable, meaning a variable under control. So this controlled variable, you have to sense it. So you have a sensor here. After that, you do compare to desired value. So this is like a reference, okay? Sometimes we use things like this. It's called set point, okay? Set point. Then we have to compare this one. We use, this is difference, then going through the control effector. So you should have a control director, control. So this is like actuator. So inside here is not just U, but probably is probably is a control variable V here. So this is a typical feedback control system. And in all the mechatronic system, you have this type of control in there, okay? For engineering analysis, you can do physics theoretical based study, or you based on experimental study. So to do experimental study, you need the sensors, okay? And most of the times you need both. So it's an iterative process. So, so features of theoretical methods to study the engineering system. So it's a general physics principle. Need some simplification, so you can establish theoretical prediction. But this is always different from the real behavior. So the model is always has a difference between the actual physical system. So we talked about this, okay? So we said that, who said that? It's all models are wrong and some of them are useful. So who is that person? G.E.P. Box. His last name is Box, okay? G.E.P. Box. He has another colleague called Jenkins. So we talk about Box-Jenkins model. So this could be very complicated. So we use laboratory facility is not required in this case, but we only do simulation. So you have Simulink, right? And in a Simulink, you have SimScape. You have semi-electricity, SimScape electrical, hydraulic, all different packages, okay? There are many different packages. So, however, a lot of time we focus on experimental methods just for the specific system under investigation, okay? So in this case, you are studying the real system. You don't have to use the simplifying assumptions. You are already running on an actual system. So we always review this is the true behavior of the system. So then for the measurements, we have to be accurate so that we have a true picture, okay? Okay. So sometimes the sensors equipments may be complicated and expensive, okay? So sometimes you cannot measure direct on the actual system. You might use a scaled model. Say, for example, you cannot put a full-scale aircraft into a wind tunnel. Remember a wind tunnel? So you put a scaled model into it. So So then we need to talk about similarity of all significant features. You have to be preserved, okay? So in this measurement method to explore the engineering principle of the system, you probably need a lot of time for design, construct, and debugging all the measurement experimental methods, okay? So there are three purposes of measurement. Sometimes you want to use sensors for monitoring, for control, or for analysis, okay, or discovery. The boundary may not be very clear cut, okay? So the category decided on may depend on somewhat on your point of view, okay? Your point of view. And apparently looseness of the classification should not cause any difficulty here. So this 1, 2, 3. So sometimes they may have some overlapping or combined, or all of them even. Okay. So we use a lot of computers for this machines and processes. It is not the critical system element in terms of either technical or economic factors. So today, everywhere you can see computer, and even your car, you have 20-some computers inside embedded. So those components external to the computer, those are mainly two categories. One is actuator, another one is sensor. Okay, so these are actually in the real systems, they are usually the main limiting factor or roadblocks for you to succeed. So it's healthy to discuss a generalized configuration and a function description of a measuring instrument. So whatever instrument you have in hand, say for example, like let's say that you have a multimeter, you have been using in the lab setting, okay? So what are the general configuration there? I think it's a good idea we focus on this picture. Okay, yes, then we see a real instrument to see what are each of the elements. So this is called functional elements of a whole instrument, okay? So we are talking about functional, not physical, okay? Not physical. What we need to learn is giving a physical instrument, how you can identify what are those functional elements like we discussed in here. So from beginning, okay, this is the beginning. You have a measured media, okay? So then here, you have the measured quantity that you want to measure. Then you will go through a sensing element, primary sensing element. Then you go through variable conversion element. Then you probably need to manipulate the variable like ×2 or do f of x, do some manipulation. I would like to say operational, okay? Like op-amp, you have some operations. After that, you send the data transmit element. Then you need to show this. It's called like display. Or like HMI. Do you know what is HMI? Human machine interface, okay? It's kind of interface. Otherwise, you don't see it, what's going on. And you should be able to store the data, okay? Store the data. Oh, sometimes you can recall, okay? I have a blood pressure meter, so they have all this type of process I can identify. So then this is the end user. So this is the user, okay? This is the user. Can see it, okay? So that's our function elements of an instrument, right? So now it is our needed ability to be able to giving a physical instrument, what are the function elements in it? So let me show you one example. Okay, so I got pressure gauge. Okay, pressure gauge. So basically you have a pipe in here, you snap this one in here, then then you have a sensor here, then depending on the pressure in here, so then your needle, your pointer will move up and down, and you have something here you can read. You can read. Of course, there's a need for calibration, so that you start to make sense of all these indicators. Okay, so I'm going to go through this strength gauge, the pressure gauge. Okay. Going through one by one. What are the measured medium? What is primary sensing element, variable conversion element, variable manipulation element, data transmission element, and presentation and observer. So here you are standing. Here is you. It's a user. We are here. We are watching this. So basically, we can do this. We can do this. So this is I. Okay, we are looking at this. So let's start from here. So the liquid is here. Okay, this is the liquid. So it's called measurement media. Okay, so measurement media, you go to the pressure is the one we are going to measure. So it's the pressure. It's the measured variable. We want to measure this. Okay, then it goes to piston. So which one is the piston? This guy. This is one body, so it's a piston, go up and down, okay? Piston is considered as a primary sensing element, okay? Primary sensing element. So primary sensing element, so this is the piston. So this is actually a conversion, go up and down, okay? Go up and down. The piston rod, this is the piston rod, actually, piston rod. It's kind of data transmission element. You transmitted the force, okay? Transmission of force. So the force is something I put arrow in here, the added force becoming on the rod, okay? The rod will transfer the force. You also have force in here, okay? In here. So that's rod is data transmission. The spring here, these are the spring, okay? These are the springs. This is called a variable conversion element because the spring, put it there, you add force, it will generate a motion, up and down motion here, okay? This is the motion, so it goes up and down motion, okay? Then you do variable manipulation of the motion, because if you have the motion, you're going to bring this one and this one. This is the pivot point, okay? Pivot point. So that called linkage. That linkage is like to transfer the rectilinear motion, up and down rectilinear motion, to through the linkage into a rotational motion. Okay, so this is a rotational motion. This is a rectilinear motion. Okay, linear motion. Okay, with that motion, we have a pointer and a scale. So this is my scale. Okay, pointer scale, and this is my observer. Okay, observer. So this scale has some of the display, those units put it there. So yeah, you do some calibration, then you can read off the scale about your pressure. So overall, you can see I have an instrument that I can measure pressure. Then you will go through all these called functional elements. Functional elements. So let me go back to show you. This is a block diagram of functional elements. So this is an example to show you a pressure gauge, how to understand this instrument in terms of its functional elements. Okay, I think this is a nice example, right? For any of the instrument you have, you'll be able to see these functional elements. So let me go through the functional elements to you again. So from the media, sensing element, variable conversion, variable manipulation, data transmission. But sometimes this could be combined, okay? If you do a, so it could be combined as one, okay? Okay, so I don't have to go through this text. I already explained it to you. So let's see another meter, okay? Another meter. So probably this is, can you recognize those basic functions, called basic functional elements. So functional elements. Again, functional elements. Okay. Okay. Can you recognize all those? So basically you have a media. This is your media you want to measure. Okay, it's a media. So this is a voltage to be measured. And you hopefully in the end, this is a display. So you have what they call, this is a paper. Okay, and the paper this paper is moving, okay, it's rolled and moving a constant speed, velocity here, so that when this one reflected the ray, you have a dot in here. So this is called photosensitive paper, photosensitive paper. So then if you move like this, so you are going to draw a trace of this is the curve, okay? So this is like a time axis, okay? So basically you can draw the voltage here. This voltage here is something like, okay? This is a T, this is a voltage to be measured, okay? But how this can happen? Because you have a light source in here, you have a fixed light source, you have a mirror in here. So then there's a rotating coil. Okay, there's a coil wounded on the frame. So if you have voltage, this ion slug will give a rotation. Okay, give a rotation. And there's a torsional spring in here. It will, if you don't have, if the voltage go away, then you will return back. Okay, so this is the whole design. The whole design. This one, N and S, of course, is called a PM. Do you have a guess what is a PM? We're going to use this PM a lot, called a permanent magnet. Permanent magnet, okay? So in this way, we will be able to record the voltage to be measured over time, okay, over time. Okay. So this is a second example, and for the transducers, we should identify there are two large classifications, two classes. One is called active, one is called passive. So when we say passive, is entirely by its input signal. You don't need a power supply. You need a power supply. So it's called purely passive. However, for active transducer, you need to have external source of power to apply to it. Okay. Okay. So remember, we see R, L, C. This is a passive element, passive components, and we see op amp. We see the op amp. We have transistors. Okay, but interestingly, diodes is not. Okay, diodes is passive, so this is active. Okay, this is active. All right, active. But you can also see transformer is not. Transformer. Okay, transformer. All these are passive, but you remember in the op amp, you need so you need the power supplies, plus VCC, minus VCC. Okay, so the output actually will be saturated by all this maximum power supply. Okay, so that's called auxiliary source of power supply. So it's active transducer. Okay, active transducer. And there are other categories like analog versus digital. Okay, so analog, okay, it has a precise value of the quantity. Okay, carrying the information is significant. So this analog, there's no loss of info. We just learned about f of t. You sample it, you get ft star. So this ft star is a sample. It's in a digital form. Okay, it's a digital form. So therefore, we lose information. Okay, we lose information. So this one has full information in that sense. Okay, the full information. So this one will actually lose information. So digital signal, basically you have a 0 and 1. So, and this is a TTL logic level. Transistor to transistor logic, okay? Transistor to transistor logic. It is between 2 to 5 is considered as 1, and 0 to 0.8 is 0. So that's a digital signal, okay? So any digital device, if you have voltage that is representing the 0 and 1, so that's called a digital device. Digital device. Okay. Yeah, because of this logic definition, we can see that digital devices are tolerant or robust. Okay. With respect to the noise. Okay. So, although individually may not be very accurate, but together it could be very accurate, depending on how many bits put together to represent. So you heard about 8-bit, 16-bit, 32-bit, and 64. So now in your Windows, everybody is using 64, but previously it's 32. I used 16-bit Windows before. In a DOS, they sometimes begin with 8 bits. So sometimes combined analog digital system is used. So in this case, it is called mixed signal. Mixed signal. So the general accuracy limitation is with analog portion. A digital part can be made very accurate. So most of the sensing and control apparatus is of analog nature. So you should have analog to digital converter and digital to analog converters, okay? So we have talked about this one in our digital control module, okay? We just finished in the last 2 weeks. So here, I think we should understand another thing about input-output configuration of measurement device. So if you have an instrument, so then although you measure, you have an output you measure, but you should understand within this measured output from your sensor instrument, you should consider that these are having two parts. First is the output component due to the desired input, okay? Desired input. So this is my desired input. We come over here, and so this desired input. And you should also consider that output components due to some interfering inputs. So this is interfering inputs, okay? So this is disturbances, okay, disturbance. But there's another thing is called modifying inputs. Internally will contribute both this side and this side. What does that mean? So say for example, nonlinear distortions, some non-ideal situations, this will actually modify my input signal. They will add towards that. So I hope you understand they are actually having 3 parts. One is called interfering input, modifying input. But what this is the desired input, what I want. But it's always coupled with the interfering input and modifying inputs, okay? So you should understand there's something, another internal. So this is kind of like internal modification of that. Maybe this is a little bit abstract. We're going to see in an example, okay? Say for example, I have an example here. So this is test specimen in here, okay? Then we put a small strain gauge patch on here, okay? Pull out 2 leads, okay? 2 leads. So that leads will give me a signal, okay? So this is a signal of my strain. Let's say this is epsilon. But this signal is very small, it's very small. I put in one arm of the bridge circuit. So this is my bridge circuit, okay? Bridge circuit. So I'm going to measure from here to here as my outputs, okay? Outputs. So I'm trying to measure, okay? So if this is balanced, so using this one to balance, to tune, to balance, to make the bridge balanced. So then you have epsilon 0. Then now you start to stretch or squeeze, then you will produce a strain. So this is a 0 strain. You have this resistance. Okay, so you make you tune this guy to make the bridge balanced. So it's 0. Okay. Then once you stretch, then this will change. Then it will destroy the balance of the bridge. You will have this one non-zero anymore. Okay, so that's why you have this. Because this signal is very small, So using this bridge circuit, why we do that is because we can use this one to achieve high sensitivity. Okay, high sensitivity. On the other hand, I have some power supply. It's called 60 Hertz AC fields. Okay, so that AC fields is my lighting. Okay, so you have lighting. So lighting will give you electromagnetic field. It's a 60 Hertz. This will superimpose on that. Okay, superimpose on that. So what is my desired input? That's the strength. It's my desired, okay? Desired. What is my interfering inputs is here. So these are the interfering inputs, okay? Because of the environment. And perhaps also temperature, maybe humidity, okay? So modifying inputs in this case, is internal to the system, internal, okay? Going all the internal elements. Say, for example, the resistor here, the resistance of this one may change over time. And this battery, okay, could change over time, okay? Because as you use, the battery will be gone, okay, get empty. So that kind of factors, okay, as called modifying inputs, will affect my output E0. So go back a slide to see this picture. So I hope you can see any sensor or instruments output here, the output here. You should understand you have two sources, okay? One is here, another one is here, okay? Here. So one is called interfering input, one is a desired input, and but another one is internal to this instrument. So you call it modifying inputs. So in a sense, you need to consider all of these. So for you to sensing sensor instrument, so if you get the E0 as a reading, you should not trust it. Okay, you should ask what are the interfering inputs, what are the modifying inputs. Okay, what are the possible sources of uncertainties. Okay. Uncertainties. Okay. Uncertainties. So you need to be clear that the sensor reading cannot be directly used before you look into those uncertainties. Okay. And sometimes the readings are not as you wished. So it's something not right. Then you should you should go back and look. So like here, you should be able to go back and look what's going on. What's the root cause of the factors causing this abnormal readings, okay? All right, so we have been talking about sensors, actuators. We started with sensors, okay? So we can see another example. This is one example talking about strain gauge setup, okay? Using a bridge circuit, you're subject to a electromagnetic field of 60 Hertz interfering and disturbance inputs. So let's take a look at this one, and you have a U2. Oh, that's interesting. It's not like that U2. Manometer for differential pressure measurement. So basically we are measuring the difference between P1 minus P2, okay, minus P2. So desired inputs are P1, P2, interfering inputs is acceleration and tilt angle if you don't put it flat. So you got something not right. And so those are external. Environmental is usually external. or environmental. Okay. For modifying inputs, usually it's kind of internal. Okay. Of course, external factors will go through internal factors to be effective, but sometimes you put all the externals as a modifying. It's fine. Okay. Yeah, it's true. So you can imagine that the G is different when you at different above sea level. So like the elevation above sea level with different height, okay? Different elevation. The gravity constant is different. Temperature, yeah. Temperature is changing the liquid and also gas properties. So we can identify these three different types of inputs. So when you get measurements about, this is a ruler, you can read off this difference. So it's proportional to that x, right? This x. So this is a second example. And now the question is giving a measurement, So you probably have three contributors, okay? The first is the real one, real. This one is interfering. Then this is modifying. And of course you have some gain factors here, right? So but it's not just the gain, okay? So we should say it's not just the gain of G, it could be a dynamic. Could be a dynamic block, okay? So what we say? G of S, right? So if you have those extra exogenous inputs and how you are going to remove them, nullifying, or just attenuate it, okay. So there are 5 categories of methods, okay? One is you just try to make the sensor that it has inherent high, less sensitive to that external interfering noises. So you change the sensitivity. Another one is you use high gain feedback to suppress all these effects. Another idea is you do a correction. You make the output go through some corrections to nullifying those effects, okay? Of course, most commonly used probably is digital filtering. You try to do some filtering. So you have heard about low pass filter, you have high pass filter, you have band pass filter, okay? Band pass filter, there are 2 types. One is a band stop, okay? Band stop, okay? And band booster. I'll show you this one later. Band stop and band booster. Another idea is just you just cancel it. You try to find out the same value just using opposite inputs. So we're going to go through some of these. Okay, the first one is called inherent insensitivity. That means you make the system less sensitive. Okay, less sensitive. So that how you achieve that is because we have a very special design philosophy in the beginning. So inherently, sensitive only to those desired inputs. So there are Fi and FMD, I'll show you later, as nearly to 0 as possible, and IM may exist, but even if you have those intermediate interferences, they will not affect the inputs. In other words, we're going back to here. So if I can design, instrument to make this thing almost 0 and almost 0. So then, of course, I only have my desired input coming out. But I'm not going. So this Fi, FMI, FMD can be designed as small as possible by some clever designs. Okay, clever designs. So. But this clever designs comes with cost, so time and cost. So it may not be feasible. Usually you already have it already, then you still have the issue how you are going to do. So the second idea is to use a high gain feedback, okay, to measure voltage EI applied to a motor. A torque is applied to a spring causing displacement X. So measure on the calibrated scale. So properly designed open loop system is simply from EI to X0. So you have 2 gain in here. So modifying input, so you have something you don't want, but it's still trying to modify you, they exist. So using a closed loop setting, so you do a closed loop setting, so then you will be able to make EI Xi to this, and this is close to 1, okay? It's close to 1. And it's less sensitive, okay? Less sensitive. So this is closed loop thinking, okay? So if you design this gain is large, so you can make it very big, so then you are not going to affect your, so in here, so you are not going to affect the others, so. So it's only affected by this one, so it's not affected by the modifying factors, okay? So it's not affected by those modifying inputs, okay? Modifying inputs. So let's see the high gain feedback thing here. So you have an open loop system like this, you have voltage EI, so you have X0 in here. So originally you are having this, but if I can find out a feedback mechanism to make this one feedback, so you can see these, if these intermediate interferences, so this will not be affected a lot to us, okay? Also, there's something here. So it's not going to affect to us because of this feedback structure, and we keep this guy big, okay? So that's another idea, okay? Otherwise, you are going to, this one will be affected to X0, this one will affect to X0, so it's difficult. So how to reduce the effects of this IM1, IM2, I introduced the feedback mechanism, okay? So this is called feedback mechanism, okay? Calculated output corrections. So you should be able to measure and estimate the magnitude of the interfering and modifying inputs to a quantitatively how they affect the output. Then you minus, you just calculate it. So, so that's another idea to do that. But the condition is you have to be able to measure or estimate the magnitude of the interferences. So sometimes the interferences are simply not possible to measure. So this method is not valid. Okay. So we want to put a little bit of emphasis in here regarding our method of signal filtering, introducing certain elements, or we call it filters, into the instrument. So their effects on the output can be removed or reduced, okay? Reduced. Any suitable signal in the instrument, input, output, and the intermediate signal, you can always try to filter them. So here is input output filtering. So you can, so then you have a interferences in here. You add a filter here. So, but I don't think this is a good idea. Okay, you probably don't have a luxury to measure this one and pass to this. So I doubt. Okay, I doubt. But in the end, we probably should be able to do something like this. So you put a filter and you just stop it, okay? Stop it. So afterwards, so this is afterwards. So instead of you do here, that's very expensive or maybe physically not possible, right? So the basic filter types, I say that everything stop is a no pass, a low pass. So ideally it should be like this, okay? The high pass ideally. So you always have this transition, okay? Transition. Remember, if you have something called 1, like j omega divided by omega c plus 1. So this is a low pass filter. So this is omega c. So this is not in the log, okay? Not in the log 10. This is also not on 20 log 10 in the dB. No. If they write that way, it should look like this. It look like 0 dB. Then you do something like this. So then your real one will be something like this. So it should look like this. If you do a log 20 log 10, you do a log 10. So this is like body plot, right? Body plot. So you can see here is pass, here is pass, okay? Then band pass is something like that. So this is pass, and this is a band stop, okay? Pass, pass. And band stop, okay? Band stop, or band rejection is also called a notch filter. Why? Because if you do a log plot, it will look like this. So it's just like a needle, okay? Like a needle. When I worked in Seagate, this is something like the depth of this one is important, and the width of this one is also important. And you know where to use this needle in the signal. You can do what? So if you say you have a harmonic of sine of omega 0 here, but I don't like it. This is my real signal. How to remove this sign? So you add this needle. It's called notch filter. Notch filter. So after you add this one, then this is the input. You go through this one, then output will give you this signal. Okay, this signal. And this harmonic omega 0 is gone. Okay, omega 0 is notched out. Okay, notched out. So in Chinese medicine, there's a thing called acupuncture. Okay, so when your system ringing like this with harmonics, sometimes called ringing, you can even hear it, you feel it. So how to remove this one? We call this this is something with sickness. So you need acupuncture, you need a needle, you need a notch. Okay, so it's very funny. So let's see an example. We just have seen the strain gauge. We did a strain gauge circuit, something like this. So then we pull out this signal, and this is our post-processing, like what we did here. We did here. We are here. We're doing a post-processing. Okay. So in this one, I can see this is a low-pass filter. It's a low-pass filter. But if you swap the position of R and C, there will be a high-pass filter, right? So in this one, we are not using a log-log plot, not in a log-log. So you don't see it nicely, but this is just a simple case. So you have 2 Hertz. It's a roll-off, and here is 60 Hertz. Of this one, I have a signal. EI is here. This is EI. Okay, this is the EI. Okay, the EI, okay, it's here actually. EI is from here to here. This is EI. And this EI is something, a signal superimposed with all these sinusoids. Okay. And this is due to perhaps my 60 Hertz power supply or lighting. And look like this. I want to remove this 60 Hertz on top of this one, and this is string only. So this string with interferences. So what you should do, you add this low pass filter, then output E0 here will remove those harmonics, okay? And the harmonics is here, okay? If you don't remove, it is 100% still there, 1, okay? But if you remove it, this one may be only like 1.1% of the, okay? So that's attenuation. What we call attenuation. So if you enlarge, you can still see something on top of it. It's not like 100% removed, not 100% removed. Okay. So if you really want to do 100% removed, you can. What you should do? You should do R, C here. Let's cascade another RC here. We can cascade another RC here. So what does that mean? It's like you have a 1 j omega divided by omega c. So omega c is 2 Hertz here. This is omega c. So if I do omega c plus 1, so this is my transfer function. If I have 3 of these cascaded, I put 3 in here. So then my rolling off is much faster. So maybe something like this. Or cannot be negative, I'm sorry. Okay, so it will be like very small, okay? So you do a high order low pass filter, you cascade another one. So the difference between the first order here, this is the first order. So it's because of this rolling off. Rate is different. Remember, we have learned for this first order, the body plot rolling off rate is 20 dB per decade. While you have third order, then you have minus 60 dB per decade. Okay, so it's different. Okay, it's different. So with that, we probably can understand much better Say, for example, I have pressure gauge and with flow restrictions. And so what I have here is, I'm supposed to have a constant reading, but I suppose I have constant range. But I have this harmonics in here due to what? Again, lighting or power, due to the power supply. I mean AC, alternate current power supply. So if I have this fluctuations, there's something called average. Average can do this filtering work. Okay, filtering work. So because sometimes the flow in here might be up and down, is fluctuating. So then you always see this. This is always fluctuating. Okay, fluctuating around a point. So we can use pneumatic filtering effect of the flow restriction. Okay, by doing that, you have a restriction here. So this is restriction. So you basically narrow the path. Okay, so that the pulsation in the air pressure may be smoothed by the pneumatic filtering. So I hope this is just for illustration. You don't have to go through an electronic low pass filter. You can use some other means. So there are another example here that is called chapter radiometer. So you have a radiant sources. This is infrared radiant sources. So this is a rotating shutter called chopper. So this is rotating this way. Okay, and this one will receive. And once you receive, you have a very small signal EI joiner. Then you put this one as AC amplification. Just put this small signal amplifier to that. But on the other hand, this chopped thing, you have an ambient light sources in here. So those ambient. So then you got your signal like this. Okay, signal like this. What you really want to keep is high frequency. To keep. And this dripping is low frequency. I want to remove this red trend, okay? And this is my TS only, so TS is here, okay? So how to do that? So you let the high pass and stop. So let the high pass, okay? The chopper frequency is here. So it get pass, so the low frequency will get attenuated. So then you'll see this signal becomes this signal, okay? This is beautiful, beautiful. So this is a high pass filter application scenario. So that's the last one. It's called opposing input. So you have idea is here. You have unavoidable interfering inputs. You cannot avoid it. But however, you can intentionally introduce some of the inputs in here such that these can be canceled out in here. Then there's nothing here. You got everything going through this. So that's called opposing input to counteract on that interference, okay? So this is called intentionally introduced inputs. You can design that. So this is opposing inputs is, I want to say not opposing, but compensating. So you try to reduce the effect, okay? So this is called a voltmeter, okay? A voltmeter. Millivoltmeter is very small signal. So what do you do here is you have a coil inside here. You have a coil, okay? The coil is hanging in here. This is a torsional spring, So then when it moves, the theta zero is the signal. The theta zero is the signal, okay? Okay. So it's very sensitive to the current applied to that. So it's possible that we can apply a compensation resistor in here. Okay. Okay. So the ambient temperature is a modifying inputs here. Okay. So we can use that to counteract on those. So this compensation. So this can be added together to cancel each other, okay? So in other words, my original R coil, the resistor is changing over time. Then I add a compensator going this direction, so the total R is constant, okay? It's constant. So that's called opposing inputs. We can have more examples like measurement of mass flow rate of gases. We have a rate gyroscope. And there are many different ways to compensate the modifying inputs. Okay. So I hope you are going to enjoy this deck of slides, have a sense of, let me summarize. We talked about the three purposes of sensor and instrument, okay? We talked about the functional elements of an instrument using a basic sensing element. We show some examples. After that, we talked about the sensor output is affected by modifying inputs and interfering inputs. Then we talked about 5 different ways of compensating those interfering inputs. And so you have 3 types of inputs in here: modifying inputs, interfering inputs, and real inputs. So we have 3 ideas. One is using the inherent sensitivity, so make it insensitive to those external disturbances. Another idea is a high gain feedback idea. Then we do a calculated output correction method. We put emphasis on signal filtering. And last, we mentioned about adding opposing inputs to compensate those interfering signals. So with these are the techniques we use this word called nullifying, reducing or compensating or attenuating those spurious inputs, including interfering inputs and modifying inputs. So these are all considered as we don't really want it. So we have some systematic ways to remove it or reduce it or cancel it or oppose it, and so on and so forth. So I'm going to pause, and the next week we are going to continue talking about more specifically on mechatronics sensors, okay, motion sensors. And then we are going to switch to actuators. And next Tuesday, I'll have my office hour. So please join me if you have questions regarding your last homework on literature survey of sensors, actuators, slides preparation. In a nutshell, we are going to have 1,200 slides prepared for sensors, actuators. So that's a collective learning experience. Okay. I'm going to give you guys some time to ask me questions, and it's time to ask. You can turn on your mic. You can talk to me. Or otherwise, we're going to see you on Tuesday. If you don't have any questions, say I count 1, 2, 3. I'm going to end the meeting. Well, Friday, and take care, everyone, and be safe, and good luck. Have a great weekend. 1, 2, and 3. Okay. Bye-bye.
Thank you.
Bye-bye.